Okay, so what we're working with today is lecture number 6 for measurement. This is based on scientific notation and significant figures. We're also going to briefly discuss accuracy and precision within this lecture. Okay, so in any of your science classes that you've had before, you should have done some studying with scientific notation and significant figures. Okay. What's important about these? Well, some people argue and say there's nothing important about these. Why do we have to learn these? I totally understand. Scientific notation is something that you'll commonly see in any math or science class, and we like to compare it to something called standard form, and that's what we normally write things in. You can put your calculator so that it gives you answers in scientific notation. You can also give it answers in standard form, but we'll understand why sometimes, even though when everything else is in standard form on your calculator, your answer comes out in scientific notation. Okay? These figures here are listed in scientific notation. Here, these two values are the same numbers from left to right, but these are written out in standard form. What's the difference? These are much more brief, okay? Really short, really compact. This has a lot of zeros represented here that maybe you don't really want to see, okay? So how can we define scientific notation? It's a short way of expressing really large or really, really small numbers, and this is based on the unit of 10. Well, what else is something that we have talked about in class that deals with, being based on a unit of 10? Well, that's the metric system. So scientific notation is really helpful when we're dealing with any type of measurement, especially when we're converting facts and figures, okay? So when we write information or we write digits in scientific notation, then we have to include 3 separate parts. So you'll see I have my digits underlined here. I have my X or my multiplication sign underlined here. And then I have something with a power of 10. And here it's 10 to the 6th power. Okay. We like to say this is 6.01 times 10 to the 6th. Okay. This here is going to be some number that's greater than or less than 1, but, or greater than or equal to 1, but less than 10. Okay, so we typically want to have some value here, something in front of that decimal point. This is, noting that we're using multiplication, so we like to say times and then some value as a power of 10. Okay, so how do we go about using this? When we write out a really large number in scientific notation, so let's start out with a number that's in standard form, 980 million. Okay. There's a lot of zeros here. First things first, you say to yourself, well, I have a really large number, and my directions say place the decimal point after the first number. So first whole number, where is it? Okay, that goes after the 9, so it's in between the 9 and the 8. Okay, and what we'll really want to do is, since we have 9.8, in our final answer, we'll drop all of those zeros off there. But what's really important is count how many places we've moved the decimal point, because remember, we assume that it's here if it's not listed. 1, 2, 3, 4, 5, 6, 7, 8. We've moved the decimal point 8 places, so my final answer is 9.8, which I put here, times 10, and my exponent tells me how many places I've moved that decimal point. Okay, if my exponent is positive, that means that my standard form number is greater than 1. Okay, if my exponent is negative, that means that my standard form number is smaller than 1. So let's take a look. When we write a small number, okay, same process for number 1. We want to put the decimal after the first non-zero number. So remember, that's a counting number, 1, 2, 3, 4, 5, 6, 7, 8, 9. Numbers 1 through 9. And drop the zeros off the end. Again, you want to count the number of places that you've moved the decimal and make the power a negative exponent. Okay, so let's take a look here. 0.00079. This is my number. So my decimal point is going to go here. after my first non-zero number, okay? Well, how many places do I have to move the decimal point to get there? 1, 2, 3, 4, 5. I'm moving 5 places to the right to get there, and that means if I have 7.9 to get back to standard form, I have to move my decimal point to the left. Notice I have a negative exponent. That means I will move my decimal to the left. Okay? Let's do some practice. Okay? Take a look. Small numbers. Okay? You should automatically be able to identify my exponent will be negative here. Okay? My decimal point goes after the first non-zero number. Well, how many places do I have to move to get there? So I know I'm going to have 5.6 times 10 to the somethingth power, and I know it's going to be negative because I have a value that's less than 1, okay? So let's take a look. 1, 2, 3, 4, 5, 6, 7, okay? I have to move this 5.6 times 10 to the negative 7th. I've moved it 7 places. Okay. Let's take a look at the next one. Again, this is smaller than 1. So I know my exponent is going to be negative. I want to put my decimal point after my first non-zero number. So that's my 3. It's going to go right here. Okay. Well, what happens here? I need to leave that because there is a digit after it. Okay. There's a digit after it somewhere. Okay. We're holding some places. 3.001 times 10 to the negative what? Well, how many places? 1, 2, 3. To the negative 3rd. Okay. Let's take a look at our next number. We have a pretty large number here. This is 6,300,000. I want to put this in scientific notation, so I know my decimal point has to go after my first non-zero number. Okay. We assume that it would start here, so how many places do we have to go from here to here? You can count either way. 1, 2, 3, 4, 5, 6. So we're going to have 6.3 times 10 to the 6th. It's positive because our number, we move it to the right to put it in standard form. Okay. Another one, we place our decimal point after our first non-zero number. So we're going to have 8.003 times 10 to the 1, 2, 3, 4, 5 to the 5th. Okay. Some little hints about going from scientific notation to standard form. Look at your exponent. It's going to tell you the direction that you need to move. If the exponent is positive, you're going to move your decimal point to the right. If your exponent is negative, you're going to want to move it to the left. Okay. Let's talk about significant figures. Another thing that you would have learned, probably the last time you heard about it, would have been in physical science. You also probably talk about it in math class, okay? There are some rules for identifying Sig Figs. We can call these Sig Figs. We can abbreviate them as SF, whatever works here, okay? All non-zero digits are significant. So this is numbers 1, 2, 3, 4, 5, 6, 7, 8, and 9. All of those are considered significant, okay? Any zeros that we find between non-zero numbers are considered significant. We like to call this the sandwich rule. That means if I have something such as this, I have zeros that are sandwiched in between two non-zero numbers, so that makes these significant, okay? Because if I look at just my non-zero digits, I have 5 and 6, so that means I have 2 Sig Figs, but because those zeros are sandwiched in, that means I have 4 Sig Figs, okay? If we have trailing zeros after a decimal, those are considered significant. Trailing means at the end. Okay? Trailing is at the end. So 0.003200. Okay? And you might say, why do you have these zeros at the end of this decimal? Well, whoever made this measurement or marked this down they're being very, very precise with their measurement. Okay, they're trying to be very, very precise. So if we take a look, trailing zeros at the very end, how many do I have? 2, and I have 2 non-zeros, so 1, 2, 3, 4. I have 4 sig figs here. Okay, after a decimal or significant. A lot of people will confuse this. They'll see something like this, 1200, 1, 2, 0, 0. And they'll say, well, these are trailing zeros. Let me fix this because it looks like I put a decimal there. They'll say 1200, but there's no decimal point. Okay, nothing is holding those zeros in, so you only have 2 total sig figs in this number. Okay, we have some rules. We're going to do some practice here in a few minutes. We have some rules when we add and subtract with significant figures. We have some rules when we multiply and divide with significant figures. Okay. When we add and subtract, we look at the terms that we are going to work with, and we count the number of sig figs to the right of the decimal point, okay? Your answer can have no more sig figs to the right of the decimal than the one with the least to the right of the decimal. So that means if I have 10.062 and I have 9.1, okay, I count up the number of sig figs that I have, 1, 2, 3, and yes, this one does count because it comes after a non-zero number. Here I have 3 sig figs, here I have 1 sig fig. So my answer, when I give a final answer, can have no more than 1 sig fig to the right. So if I do the math, 19.162, I have to cut my answer off here. Can you round? Absolutely. 19.2, okay? When I multiply or divide, I want to count the total number of sig figs in the problem. We can do the same thing, 10.062, whoops, and I want to multiply that by 9.1, okay? Your answer has no more sig figs than the least number of sig figs. Well, let's take a look. 1, 2, 3, 4, 5. I have 5 total sig figs here. I have 1, 2 sig figs there. Okay, my final answer can have no more than 2 total sig figs, and a lot of times this is where scientific notation really becomes important. 0.62 times 9.1. This gives me an answer of 91.5642. If my answer can have no more than 2 sig figs, I'm going to have to ask myself, what can I do? Can we round this to a whole number? Sure, we can make this 92. Or people a lot of times will say 9.2 times 10 to the first. People will give answers like that as well. Okay, let's do some practice. Okay, let's do some practice. Let's count up our number of sig figs. 1, 2, 3. Why do I say 3? Those are all non-zero numbers. Okay? These are all non-zero, 2, 5, and 1. This is sandwiched in, so we have 4 sig figs. Okay? Here's a decimal point. You see that these zeros are sitting here kind of as placeholders, but we can't count those as being significant because there's no non-zero number in front of it. So we only have 1, 2 sig figs. Okay? Number 4, 92, and then we have 2 zeros after that decimal point. These do come into play because these are considered those trailing zeros. They are significant because they come after non-zero numbers before the decimal. Okay? And then here we have 2 sig figs. Okay? Look at number 6. This is a problem very similar to a lot of people get this confused. I see 3 zeros and a 1, and a lot of people say, well, these zeros are after a non-zero number, so I have 4 sig figs. It's not true because there's no decimal point in place there, so you only have 1 sig fig. Well, let's look at the rules for adding, and subtracting, and multiplying, and dividing. Okay. So 33.2. And to that, I want to add 2,051. Look at what you wrote down when you add and subtract. We want to count the number of sig figs to the right of the decimal. Here I have 1. Here I have 0. There's no decimal point, so I have no sig figs to the right. All right? You plug this into your calculator, 33.2, I apologize if that's going to zoom in and out, plus 2,051. That gives me a number of 2084.2, okay? But we have to pay attention to Sig Fig rules, so we can't have this here. Just chop it off, okay? Next one, multiplication and division. We want the number of Sig Figs as the value that has the least. 1, 2, 3, 1, 2, 3, 4. So I want my answer to have 3 Sig Figs, okay? So we want to do 33.2 times 2,051. That gives me a pretty large number, 68,093.2. I want 3 total Sig Figs. You notice I have a lot here, so that scientific notation will come into play. I want to put my decimal point right here because I can have 1, 2, 3 Sig Figs there, right? So 6.81 times 10 to the 1, 2, 3, 4 times 10 to the 4th. Okay, we'll do more practice for these in class, so don't worry if you're feeling confused, but make sure you write these examples down, okay? Back to adding and subtracting, 0.0032. To that, I want to add 92. For our rules, we want to look to the right of the decimal point. I have 2 Sig Figs here. I have 2 Sig Figs here to the right of the decimal point. So I only want my answer to have 2 Sig Figs to the right of the decimal point. Okay. When I plug this into my calculator, I end up with 92.0032. Okay. Excuse me, I want 2 Sig Figs to the right of the decimal point. Does this round up? Nope. 92.00. Okay. And then lastly, same thing. Let's look at our total number of Sig Figs in our possible work. We have 2 Sig Figs here. We have 4 Sig Figs here. So we want our answer to have what? The least number of Sig Figs. 0.32 times, 0.0032 times 92. We plug that in our calculator and end up with 0.2944. Okay. I want 2 Sig Figs. Here we are, 0.29. The last part of this lecture is inclusive of accuracy and precision, and these are 2 terms that you've probably heard so many times together. But what is accuracy? So accuracy, how we are, or so how close, we could say this is how close we are to an accepted value, and precision is how close measurements are to each other. Okay, how close they are to each other. What's the difference? Okay, easiest way to explain this is always with a set of bullseyes. Okay, I have 4 drawn here. They're pretty mediocre in terms of being artistic. But if you look at this very top one, I'll call this number 1, number 2, number 3, number 4. So I'll go counterclockwise. Notice all of my dots on my target are really close together, but they're not in the bullseye, because we know with like a dart target or a dart bullseye, a dart board, the bullseye in the center is the desired place to throw your dart. So we have very low accuracy here because these are not anywhere near that bullseye, but it's very precise because they're all close together. Okay, let's look at number 2. These are scattered all over the place. They're not bunched up or close together, so low precision, and they're not all consistently by the bullseye, so low accuracy. Okay, look at number 3. These are all fairly close to the center of the dartboard, so they're fairly accurate, but the precision is a little off because we have some outliers here. Okay, number 4, these are all revolving around the center or around the bullseye center itself. So we're very accurate and we're very precise. I know they're generic drawings, but hopefully they are beneficial we are going to do tons of practice, especially with a little Nerf gun in class.